Hi everyone, my name is Eduardo Murcia. I am a master's student at the University of Florida, of course, and today I will be presenting what is part of my project and the part of my research as well. I work with time series data, doing forecasting. So let's start. I will present hybrid machine learning and implementation of a mixture of experts ensemble algorithm in soil moisture forecasting tasks. Okay, so now let me explain a little bit about the problem under study. Well, in my lab, we work with soil moisture sensor data and we work with growers. We provide recommendations to them, we provide decision support system to them, and what we have found that we need and that will be convenient for us and for the growers will be having an accurate forecasting system so that we can have a more planned irrigation scheduling. However, we have been trying for some years, all my lab working on that, and we have found some common issues on this when we are trying to implement that forecasting system. And those issues come from the data because the time series that we collect from the soil moisture sensors are extremely noisy. They have a high dimensionality, they're non-stationary, and they are non-linear. So those characteristics limit the implementation of any kind of technique, either pre-processing or machine learning or any modeling technique. So, another thing that we have found is that when we are doing we are trying to do the implementation of the forecasting system. None of the algorithms actually work. There is no single algorithm that can perform in the way that we need that. And this is not only as there is a lot of literature review that has been done in terms of is the way to move forward. And even though they have tried like really impressive, the more advanced algorithms in machine learning, deep learning have failed at least when they are implemented in a massive way, in a representative way, not with only one or two time series. Like when there are some competitions that have tried the M competition, they have implemented algorithms in thousands of time series, and they have found that not single algorithm can actually provide the results that we need. And the way that they have suggested to move forward is using hybrid approaches. And when I say hybrid, it can come in two ways. One is using combining signal preprocessing techniques specific for time series with modeling, and the second one is implementing ensemble algorithms. And there have been like efforts on those two aspects, and like of course many there are many variations of them. And well, in the existing approaches, what I will present today is, as I say, there is a lot of research. There have been like many interesting applications in terms of using not only machine learning, but yeah, machine learning and deep learning algorithms uh, that have been interesting. However, we still need uh, we keep investigating so we are actually able to bring down that barrier. And today I will be talking just about my previous stage in my research. As I mentioned, I was have been working on this project, and we implemented a previous stage that provided some interesting results. That was combining signal preprocessing techniques, signal decomposition techniques, with some time series forecasting algorithm. That was a LSTM with an encoder decoder component and random forest. So as you can see on the right panel, we observe some interesting results. The blue line, which is the predicted one, has this like has been able to nicely capture all the most structural components of our time series. However, after the time step number 100, we observed that the performances start degrading, and so after that point, we cannot rely on it anymore. And so, because of that, is that we realize that we need another way to move on, and the way that we have been thinking on is implementing not only one algorithm at a time, but implementing the like several of them, because we know that each algorithm is able to specialize on different regions of our feature space. So that's what we are intending to do. And this is the proposed approach. There are so many, like there are several ways of integrating multiple algorithms. One of those is a mixture of experts. So what a mixture of expert is, well, uh, they are just a nice way to combine different models and to make them to focus on different regions or aspects of the input space. And then what it contains is a series of experts. In this case, we have three of here, and then it has a gating network. That in our case, we are using a mixture of Gaussian components for that gating network. And this gating network is responsible for determining the weights that are assigned uh, to each expert on the given input. So what it does is compute the probabilities of each expert being the most appropriate one for each one of the points that we pass in the input data. This modeling is because we are using the Gaussian mixture model. This modeling is done throwing a Gaussian distribution over the components, and each distribution represents one of the experts models. And and then we have the gating network, and the gating network has the parameters, and in this case will be the mean and the variance of the distribution. And the outputs of that is the distribution of so what it does is then the gating will provide the final forecasting. That will be a combination of the different algorithms. And we have our point prediction as output. Over here you see these experts. I will explain why I did select those experts in my methodology. So in the experimental designs, after passing the first stage of checking on the quality of the data and everything, all the exploratory data analysis that we regularly do, we went into building the mix of expert architecture. And for that, what we first did was set all the structure of that um, model. And so, as I mentioned, we have the experts, we have the gating network. So we like how many experts we are using. We define the architecture of our gating network, that in this case will be using a Gaussian mixture of components. And then we combine those two to form to start the mixture of experts. And then we do like the respective calls of the experts and the gating network. And then we compute the weights that will represent the probability of a model to switch the input data, and then return associate that to an output of our prediction. The algorithm that we are using for updating all the variables for both the experts and the gating networks in this case is an expectation maximization algorithm. So in the first step, in the expectation step, it computes all the responsibilities of the models, and then in the maximization step, all the parameters are updated using the gradients of that provides that are calculated inside the algorithm. Let me go a little bit over how we selected the experts. We started with simple one with a shallow feed for our neural network, and then we start checking and doing quick experiments to check the performance of them. We realized that it did not perform well, so we started adding some dropout layers, making it less shallow, like a deeper network, switching the kernel initializers, adding clipping gradients, playing with the learning rates. And then we did not find that like any significant improvement, so we have to move on a different type of network. We include an encoder component. We also, and we did all the same process. We also play with a convolutional neural network that did not provide the expected results. That was a bit surprising. And then we have the last three that are the ones that we selected. That was long short-term memory with an attention mechanism, the same but using a GRU instead of the long short-term memory. And the last one that is a transformer-based attention mechanism that has a multi-head component that uh, becomes convenient for processing multiple parallel tasks. Uh, well, all those three has something in common that they are pretty good at keeping information in long-term dependency. So uh, that's a common characteristic. And then when we selected the expert, after we selected the experts, we went into doing the hyperparameter tuning. For that, we use the framework known as Optuna because it provides an efficient way of doing that rather than using our own code, and this is way more faster and efficient to use Optuna. So with that, the parameters that we use were the learning rate, the kernel initializer, the dropout rate, and the activation function. We selected those parameters because we have limited resources, so we have to filter out which parameters to pick. We did not play with the shape of the shape of the networks because that can become a little bit of an issue if they are not compatible. So what we selected the learning rate because it's the most important one, the one that can contribute the most. And then also we selected the dropout rate because all our network has some layer with dropout. So we were playing with the rate of that. For the training and validation, because this is a time series forecasting task, we do not use regular cross validation. We use forward validation that is just respecting the order. And for that, we build windows of this red uh, box will represent a window of 500 time steps, and then we do the forecasting in the next. We use for training the data, doing training and validation, and then we move on. Irregular, like usually, or what is recommended is to use one time step at a time. However, because we were using 10,000 time steps in this exercise, it was too expensive for implementing the routine of the hyperparameter tuning. So we have to reduce that. That reduces the capacity of the model of learning some features, probably. But for the sake of the computational cost of this exercise, we have to do it. So we implemented 50 time steps. We move on, so we every time. And for the test, well, we used we at the beginning of the experiment, we did a split. We used the first 10,000 times test for training and validation, and the rest for test. And in the test set, as you will see in a few, we load the model and we use the mean absolute error and the mean square error for determining the performance. Well, let me explain a little bit about the performance. What we found, unfortunately, we did not find what we were expecting. One of the first thing that we found was that the stability of the algorithms was not the best when we were doing the training after doing the hyperparameter tuning in selecting the best parameters. We were training on the entire training data set, and when we were repeating the results, the performance of the model was pretty unstable. The convergence was not guaranteed every time. Sometimes it just blew away. And we tried to change the kernel, we tried to change the optimizer, we switched from AM to stochastic gradient. That I mean, also one of the issues as well was that it was getting stuck in local minima. So we switched from AM to stochastic gradient descent, and it helped, but then it increased the instability of the model. It was sometimes converging, sometimes wasn't converging. And also, like, the performance of the model is, you see the mean square error and the mean absolute error are high, especially the mean square error, and that makes sense in when we would see the results over here, for instance, because we see that sometimes the model is decent, it's pretty decent in capturing a small variation of our data. However, we have these areas where it just goes away. from the real value, and those outliers impact more the mean square error than the mean absolute error. And that's why sometimes, for instance, here we have really high mean square errors compared with the mean absolute error. That happens every time in all this. Oh, well, this is something that I did not mention. We implemented this in three different datasets, like repetitions. So we did three times everything, and these are the with three different sensors, and these are the three uh, forecastings that we did with every sensor. With the first sensor, we have the results. We have it's not too bad, but for instance, in the third sensor, we have like really bad results. The model was not capable of performing really well at all. Um, well, so the conclusions, the results indicate that the mixture of experts could only capture certain features of the input data. For the three data sets that we were using to train and evaluate the performance of the mixture of experts, we observed high instability on the convergence of the model during the training. Really had some like, relatively high mean square error and mean absolute error on the training and the test set. And we observed the presence of uh, those really outlier forecasting values that are out of their range. However, well, what our initial hypothesis was that using a mixture of experts that will create local experts in the feature space of data will help. For now, we have to say we couldn't prove that theory, that hypothesis. However, we do not discard entirely this approach. There have been interesting applications of this. This is one of those. So this is a paper. I recommend you to follow that. It's the mixture of expert probabilistic forecast of aggregated time series, and they provide all the code for running. And it's a pretty interesting paper, and they were successful on implementing that. So what we found out is that we have to modify our approach. One of the things, for instance, is that we were doing the training and of the experts and the gating network in parallel, both at the same time. This is because that is expensive. We have to limit the training of the experts, for instance. So what one approach could be switching to bring to pre-train the models, have all the pre-trained models, and bring them into the mixture of experts, and uh, focus the second stage into training the gating network rather than the experts. One other approach could be, of course, well, besides trying new algorithms instead of change the experts models and playing with all the hyperparameters. Another approach could be switching to another type of gating network. There are more advanced gating networks that could improve the performance. So, for instance, that is one of the things that they do. The gating network that they use is a neural network that is deeper, and maybe that could help us as well. Okay, now let me just show you my code. I did an implementation using I work in Collab. I have all my data uh, in my drive. So I first install all the Optuna framework for doing the hyperparameter tuning, and then I import all the different libraries that I was requiring, and then I import my data to one of my datasets. This is for the first sensor, and then I have this function. The first one is this one is in charge of doing the split between training and test set. Then we have this one that allow us to change from vectors. That is the format that we get the time series into tabular data. That is the shape that we need inside the model. Then we have this. That is the uh, mixture of expert itself. So what it does is first we have the three experts. We set up all the architecture of the experts. So for instance, the first one is the LSTM with the attention mechanism. The second one is the the transformer based model, and the third one is the GRU based model. So all of them, as I was mentioned before, I implement. were implemented with some dropout to improve the generalization capabilities of the model. We set as a hyperparameter the kernel initializer and the activation function in the input and some hidden ledgers of our networks. In some for the final layers of our model, we did not set a hyperparameter. We just fixed the kernel function and the kernel initializer and the activation function. And then we have the gating network. Over here, we have first the definition, like the gating is taking as input all the outputs of the model, and then it set up all the parameters of the gating network, which are the parameters of our distributions. And over here is where all the Gaussian mixture of models is happening. We see that it's throwing a distribution on the input data to determine the probability of a model to switch a certain point of the data. And then, well, we define all the weights, so all the that will be representing the contribution of each model to the data. We have this function as well, that is the loss function. In this case, we were using mean squared error. One of the things that we also implemented when in our experimental phase was switching from mean squared error to doing the optimization of the on the distribution of the data itself. In time series, there are some papers that have suggested that in time series doing the optimization on the data distribution itself using, for instance, maximum likelihood, an MLE approach could become could be better, but we did not observe any improvement, and so we came back to mean square error. We implemented a scheduler as a breaking point of our routine as well. So every time that the, the learning rate went below a certain point, we just stopped the training. And this is just the sliding window split. The, this is the function that allow us to format the walk forward validation stage. We have our objective function, that is the function that allow us doing the hyperparameter tuning. As you can see, these are the hyperparameters that we are defining: the dropout rate, learning rate, activation function, and the kernel initializer. Something interesting to mention is that we were normalizing the data, as that has a beneficial effect on the performance of the model. On the optimizer, we switched from different ones. We tried the Adam at first, but then it was getting stuck in local minima. We tried the stochastic gradient descent with momentum, and that helped, but it also increased the instability of the model. So we tried also the NNG, the nested up optimization algorithm, but it was pretty similar to stochastic gradient descent. And this is where the expectation maximization process is happening. Over here, we compute the responsibilities of each expert, and then we have the maximization steps, where we first compute all the input, output, and loss of uh, values of the experts, and then we calculate the gradients, and we use the gradients to update the parameters of the model of the experts. And then we do the same with the gradient network. We compute the parameters, we compute the loss, we compute the gradients, and with the gradients we update the parameters. Well, this part over here that you see is where we are using the implementation on the different windows, the validation, the walk forward validation stage. And well, here is where then training during the hyperparameter tuning process happen. You see, like there are loops inside the loops, so it's a really long stage. Finally, we found our parameters, so we found a dropout error of uh, 0.33 in this case. It's a pretty high uh, well, not sorry, a dropout rate of 0.33, a normal dropout rate. And then we have the learning rate that it was 0.008, which is uh, like not too low one, not too high, it's a regular one. For as an activation, we use the ReLU, and we in this case we did not use any kernel initializer. It was not the same in every case. And then we do the final training on the using the total data, like all the entire training data set, and we get our results here. uh, well, we finally found our mean absolute error, I mean mean square error. As I was mentioning, it's not too bad, but it's not the best, and especially the mean square error is a little bit high, and that is happening because of the outliers, so like all those extreme events that are being forecasted. And then we have here our test function that we can run. So this is importing all the data, the libraries. Then we import our data set. Then same function that we were using that I explained before. And then uh, we run uh, the training stage itself, as you can see, and we get our final performance on the test set. And finally, we can visualize our results in the plot. So the blue line is the actual values, the red lines are the forecasted values, and you see those are our issues, because in this region the performance pretty well, pretty nice. This one is the same, but we have those issues where we are not getting the best results. Well, that's it. Um, if you want to find more information, please follow the GitHub link that is attached to the description of the video. Um, Thank you.